1a, we have to list the functions below from the lowest to highest order, right?
You mean what? Are you talking about the makeup exam or?
Yeah, makeup exam 1a.
1A. Okay.
Yeah, we have to list the lowest to highest order, right?
Yes.
It means like we have to list a lowest to highest order. Like we have to consider n, O n, or O log n, something like that.
Okay. Yes. So n log n, right. N square, n factorial, right? You understand what is the fastest and what is lowest. So I have 16 functions in here. So lowest to highest order. Lowest means the fastest one. Highest order is the most complex one. Okay, is it clear?
Yeah, and can I ask another question on number 3?
Number 3, go to number 3, yeah.
I'm not sure what you meant by design a data structure.
Design a data structure to support the following. So the question says support the following operations. So insert. So if you structure, let's say you wrote in the tree. Okay, if you make your data structure as a tree, insertion take. How long does it take? Okay, that will take some time, right? Deletion will also take some time. And member is just checking is it existing or no. Okay, that's your decision. You can say, oh, okay, I choose the data structure as a tree. Then here's my proof. By doing insert, it takes this time. By doing a delete, it takes this time. And by checking members in the tree, it takes this time. That's what I meant.
Okay, all right, thank you.
Okay, thank you. So if you're doing homework, so you are allowed to use the material, but don't try to do the Google it and get the answers from the Google. Okay, try to digest and express your own way. If you copy from the text, if you copy text from internet, then this is obvious. I can detect it, right? So don't do that. Don't just copy from the internet. Digest, then express in your own way. All right. Okay, so and it is very difficult to make an exam when we are doing online, and it is all take-home exam, right? So be more careful and try to submit it on time. And any late will be counted as 1 day late. 1 day late, 1 day late is 10% point deduction every day. Okay. Any question about the makeup exam? No, everybody clear about this? Okay, so I uploaded the program practice number 4, and today you're going to have a practice number 5, and it is both of them are due on next Monday midnight. And if you're doing the makeup exam at the same time, there will be many jobs to do, right? So be hurry, start early, then you can eventually solve it, right? All right. Any question about the program practice? No. All right. Thank you, guys. So try to follow the web page that we are sharing. And today we're going to talk about BFS. So last Monday we talked about BFS. Okay, we know the concept of BFS. Now today I want to talk about DFS, depth first search. Okay, let's solve this problem. Let's warm up our brain. So POD, problem of the day. So prove that in a BFS on an undirected graph G, every edge in G is either a tree edge or a cross edge. Whereas cross edge is an edge where X is neither ancestor or descendant of Y. Okay, so if I give
Professor,
you, yeah.
We cannot see the slides.
Okay, sorry. Thank you. Can you see? Can you see the slide?
Nope.
No?
I think you haven't selected the screen that you're sharing.
Screen. Share. Why is it? You are sharing your screen. You are screen sharing. You're not able to see. What do you see? Nothing.
We only see the caption. Like Jihindru has started screen sharing, and that's it.
Oh, why is this happening? Maybe low bandwidth. Let me stop sharing. Then let me share again. You're sharing screen.
Yep, now it's here.
Now you can see. Okay, sorry. I think I clicked multiple times, then making some error. So, problem day. So prove that the BFS, the proof in the computer, the analysis algorithm is persuade me. Okay, understand and persuade me. So prove that in the BFS, on an undirect graph G, every edge in the G is either a tree edge or a cross edge. Whether cross edge is an edge where X is neither ancestor or descendant. So you understand the problem, right? So this is the edge. So if the edge is the part of your tree, that is tree edge. If the edge is the edge from like ancestor to the descendant directly, this is called the forward edge. If your descendant goes to the ancestor directly, this is called the back edge. Cross edge, either of them. Not a between same sibling, or these are not connected, but this kind of edge called cross edge. Okay, so remember this. And let me copy this. Okay, so let's solve this. So can you see? Do you understand what we are solving? So we need to solve that the BFS. If you're building a BFS, it'll be either tree edge or cross edge. There is no back edge. There is no forward edge. Let's think about this for 5 minutes, and we can solve it together. Do you understand the problem, right? Everybody? So if I repeating, so you understand what is a BFS, breadth first search, right? While you're doing this in the graph G, so every edge in the graph G is either tree edge or cross edge. There's no back edge. There is no forward edge. Okay, is it true? And why is it true? Okay, let's think about for 5 minutes, and I'm gonna choose the student. So I'm going to ask Roshan, Yejin, Adrian, and Jungmin. I think Dayang dropped the class. Dayang and someone else. Kelly, I think. No. Okay, so ready? Oh, for the start, so for the auto records. So what's your solution? Jungmin?
Yes. So
Okay.
I'm not sure, but I think so when an ancestor of the node is detected, then like that is, it means that it's not a tree edge, right? So so it means that like breadth first to search did not like find out all the nodes at the previous level.
I'm sorry, hard to understand. Okay.
Yeah, but I'm not sure.
Okay. Don't worry. I love to hear
try.
I love to hear the crazy idea. So what you are saying is you're building the tree.
Yeah.
In the process of building the tree. Then what?
Then like from the tree edge, when the ancestor is detected, it means that the breadth first search did not like find out all the nodes at the previous level.
Oh, all the level did not find out. Okay, maybe let me revisit to you.
No. You give me more time.
Okay, all right. So Adrian?
Yes.
Okay.
So I think you can prove it by using contradiction.
Okay.
So let's assume that like contradiction that so every edge in G is either a tree edge and a cross edge, right?
Okay.
So if we draw a tree and then we use BFH to iterate over the tree, then if there is connection from vertices A to B, then they are of one level, right? So that means it is a tree edge.
Let's think about this graph. Let's say A to B, C, D, E. So let's say I'm building tree out of this graph, say starting with the A, then B and C. B and C. From B to C, B to D, right? B to D, and C to E. Then D to check to E, and E to check to D. That's pretty much it, isn't it? B has, see, A has 1, 2, A has 1, 2, B has 1, 2, 3, B has 1, 2, 3. C has 1, 2, 3, 1, 2, 3, C to A, and C to B, and C to E, and D has 1, 2, E has 1, 2. Okay, so now you're building a tree out of the graph. Okay, let's start from here. Adrian?
Okay, so from there, then by using BFS, then from A, it is connected to B, but not to D, right? If it is connected from A to D directly, then it is not a cross edge, right? So since BFS goes to every edge that is connected to the vertices, so it will be either a tree edge or a cross edge. It will not skip the child.
So you are saying if the A and B there was a connection, it won't be like this. It will be like this, right?
Oh,
so in the VFS, it is not able to make forward edge. Clear? In a BFS, it is not able to build a forward edge. At the same time, same thing, like D to A, if there is an edge, D to A, this is not possible, because if it was like this, it should be already either like this or coming forward edge. Forward edge and backward edge is not countable. It's not possible in the construction of the BFS. Okay. All right. So anyone else can prove in much nicer way?
I want to try.
Okay.
So we're proving that using BFS of an undirected graph G, every edge can be either a tree edge or a cross edge.
Okay.
The claim that an edge can be a tree edge is trivial, because if I build a usual graph that does not have any cross edges or forth and back edges, it's going to be a tree edge, because that's the structure of it. Correct?
Okay. Okay.
Then we have the second choice, which is a cross edge. And the cross edge states that a cross edge xy is an edge where x is neither an ancestor or descendant of y.
Okay.
Which leads us to back and forth edges.
Okay.
Considering that we are using BFS, while building a tree, we cannot access back or forth edges. Thus, it leaves us with cross edges.
Okay. All right. Great. Anyone else? Okay. Thank you, Janar. So let's prove it. So when we're building from a random graph, G, let's say there is a multiple edges are there. So whenever we're building it with the BFS, what do? I start with this. I'm checking all my edges, right? Then I build. The forward edge, something like go to from here to there, right? That is forward edge concept. Okay, I want to have like this. Then it should be one hop there. But if there is this edge, this link was existing, then it should build like this, right? Therefore, in the concept of the BFS, this forward edge is not possible, okay? And how about backward edge? Backward edge, oh, while we're doing this, I want to have this reverse way, okay? As long as we have undirected, this concept is same as the forward edge. Therefore, we are not able to have the backward edge, back edge. Then what about the cross edge? Erase. So cross edge is something like this. So this one and this one. Now I built a two. Then maybe I can discover this guy. But the multiple hops, then I can give you. But at the same time, if there is an edge between two, then I can check it. Then make it may turns out it is discovered already, meaning it's part of my tree, or you are my cross edge. This is possible, right? So let's say there's a link between two, then what do? Starting from this guy, me, then I discover my neighbors, then I discover my adjacent, then I can also check this. Oh, you are my cross edge, but you are in my tree. So you define it as cross edge. So it is possible. So we check the 4 cases while we're building it. So all the edges either in tree edge or back edge or forward edge, cross edge. In a BFS concept, we are not able to have this. We are not able to have this. If this has happened, this should be this level. The same thing happens to here, forward and backward. Okay, that is why in the BFS it is not it is only have the tree edge or cross edge. How about DFS? Okay, we're gonna talk about in the lectures. Let's continue. Okay, so connected component. What is connected component? So connected component in the graph G, let's say everything is discovered. So let's say your whole plane, they are separated. They are somehow separated. Separated meaning they don't have connection between these two nodes or these two nodes. Meaning I have connected components here. I have connected components here. All right. So connected components over undirect graphs are the separate pieces of graphs such that there is no connection between two pieces. Pieces, in the pieces, they are all connected. There is connected components, okay? It's many seemingly complicated problems reduced to finding or counting connected components, okay? So if it is solvable, it should be a connected problem. If it is separate, meaning I'm not able to go there. Let's say there is an island, there is no bridge. So I travel by the car. So that component is not connected because I cannot go to there unless I change my transportation. Okay, same thing. So we are reducing the complex real world problem to the graph problem by converting to the graph and by converting to the mathematical problem. It is much simpler, then we can solve it, then you can reply back. Okay. So for example, testing whether a Rubik's Cube or 15 puzzle can be solved from any position is really asking whether the graph of legal configuration component. What does this mean? So let's say, so I'm sure you know about the Rubik's Cube, right? It looked like 3 by 3, and there is many cube and position. Okay, so let's say it is completely done, meaning all faces with the same color. What's the rule of the Rubik's Cube? And what do you mean connected component? Okay, from the Rubik's Cube, with the one move, how many possible? Maybe 6 of them. If I can tell you more, then it will be 12 or 10, right? So it has 1, 2, 3, 4. 1, 2, 3, 4, 1, 2, 3, 4. 4 times of 4, 16 possibility. 16 possibility from the done position, completely done. Then I can make one move. Then from one move, the figure, your cube look a little different from this one by the one move. Then you may have multiple configuration of the one move. With the 2 moves, you may have the multiple configuration with the 2 move. 2 move, 3 move, 4 move, 5 move, right? In the end. So if your move is complicated with the previous, then I don't need to add it. Okay, meaning I don't create the baggage. Do you understand? Okay, that means connected components in the Rubik's Cube, meaning a legal component. Let's say I'm breaking with the forces and I assemble it and somehow differently. Then I give it to the pro. Pro may think, I think I cannot solve it. How do you know that you are a pro of the Rubik's Cube? Then why is it not possible? Because that move is illegal. Okay, so how do they do? So if you look at the, let me show you a couple of slides, a couple of video. Rubik Cube. Clear. Uh, 7 years old. So let's look at the speed of the Rubik's Cube. Okay, so they watch it, meaning they figure out their configuration. And they testing it, right? If I break it, if it assemble with the forces, they won't be able to. Then how they do? Right? Because they know the rule. What needs to be done? They know the level. Okay, rolling back with the backtracking, then they can solve it in 6 seconds or 7 seconds. Okay, if that is not your possible move and move. They don't do that. So we have steps. How many steps done it? And they figure out, okay, that is 17 steps of root 5. Then they're rolling back 16, 15, and 2, 1, then they finished. Okay, and that is why it is possible they can be done in a short second. Okay, so that is how the Rubik's Cube works. So anything discovered with the BFS must be part of the same connected component, because they can do, because it's the same connected component. It's one move. Then we repeat the search for any undiscovered vertex and to find the next component until all vertices are found. So if we apply our BFS to Rubik's Cube, okay, BFS one move, second move, third move, fifth move, okay. All right. So implementation of the BFS, then you can do this. Initializes the graph, and you are visiting all the vertices. You are visiting all the vertices as long as it is undiscovered. Discover is false, meaning undiscovered. You are keep doing a BFS. Okay. Then let's think about the two coloring graph. Two coloring graph meaning I want to separate the two teams from a one team. Meaning I want to make a graph problem. So let's say I want to divide the CSE373 students to the two groups with the two different colors. How can you do that? So I build a tree, and each level 0 is one color, level 1 is second color, level 2 is a 0 color, black, white, black, white, black, white. Then I can bipart the whole graph. Okay. So this is very common problem in the real world. Graph is biparted if it can be colored without conflicts while using only two colors. Bipartite graphs are important because they arise naturally in many applications. Okay, so any edges, if there is an edge, they should not be connected by the same color. So if I build the legal tree, then I can do that, right? Let's practice. 1, 2. Let's say there is many edges. Say I want to build a bipart two coloring graph. Let's say I color as a block. Then next one is green. Then this link is my legal. Then these two are black. And this line is my legal. And this is green. Let's say this is illegal. Then it will be black. Okay. Then I can make this green from this link. And I can color this guy as a black by this link. Okay. Meaning that I can delete this link, this link, this link. Then I colored every vertex with different color. Any of the adjacent are not in the same color. Okay, this is basic two coloring problem. From the graph, I can build a two coloring vertex. Then I can solve in this way. It's something like this. And it's commonly solvable by the BFS. Okay. So what we just did in the previous slide, and we can augment BFS so that whenever we discover new vertex, we color in an opposite parent. So we just observe it, right? So initially, we do uncolored and set the bipart as a true, initialize a graph. Okay, this is where the algorithm starts. From all vertices, if it is not discovered, I color the white, then go to the BFS and go to the BFS. Okay, starting with the white and go to the BFS. Then this BFS function gives me processing edge. If there is an edge, okay, then I can set it as a false because the color of the color is the same. Therefore, I complement the color. Okay, then complement meaning when it's white, convert it to black. When it's black, convert it to the white. Okay. All right. So we see how we do this. So do we have more slides? So basically, initialize the graph and color the white color started one edge, color to the different color to different color, and color to different color to its parent. Okay. So we can assign the first vertex in any connected component to be whatever the color or gender you wishes. Okay, something like that. If it is set to white, then my children will be black. Their children's children will be a white. And you can, so like the pictures that I draw in here, then we can understand that, right? Then this is how you do simply. Then let's talk about DFS today. So DFS has a next neat recursive implementation would eliminate the need to explicit use of stack. Okay, so discovery and the final times are convenient to maintain. This is the advantage of the DFS. And key idea with the DFS, a depth-first search of graph organize the edges of the graph in a precise way. In a DFS and DFS of undirected graph, we assign a direction to each edge from vertex to each discovery. Let's do this. Let's say I'm starting from this guy. 1. What does this DFS do? Okay, go to 2. 1, go to 2, then go to 3. 3, go to 4. 4, go to 5. 5, go to 1, which is back edge. 5, go to 2. Oh, that's back edge. Then checking, mark done, processing done, processing done. In here, then I go to 6. Okay, this is how the DFS work. How about BFS? DFS starting this guy, then 1, 2, 5, 6, 2, 5, and 6, 2, 5, 6. From 2, 3, 3. From 5 is 4, 5 to 4. 5 to 2 is cross edge. And 3 to 4, that is cross edge. Right. So there is nothing to discover, so it's all processed. So 6 was done because I have nobody to connect it, and 5 starting from 4. 4 is done. I have nothing to do. And 3 roll back, 5 no back, 2 roll back, 1 roll back. Then everything processed. Okay. So for example, this, I think this is a nice example. So DFS, I have a back edge and the tree edge. BFS, I have tree edge and the cross edge. Okay. Now we know the concept of a cross edge and the back edge and forward edge. All right. So this is the exact the same way. Then we can build a DFS. Okay. I'm assuming you know the you know better than me about the DFS. Okay. So this is the one nice example of the DFS, the maze. So how do you escape from the maze? So if it's blocked, then roll back to the last point. Keep doing this. And if you're stuck, and roll back to the last decision point and comes back and roll back to the last decision point, then take a different path. Okay, roll back to the last decision point. Roll back to the last decision point. Roll back. Then you can escape. Okay. So one nice example of the DFS is the maze control. Maze escape. Okay, so edge classification of the DFS. So every edge is either a tree edge or forward edge or back edge or cross edge. Oh, we just discovered it, right? On a particular DFS or BFS of the directed or undirected graph, each edge gets classified as one of the above. Okay, so edge classification implementation. So if the edge is parent, let's say I'm discovering, let's say I'm building a new tree and doing an edge classification. I just found the classification X to Y, X to Y. Then the parent of Y is X, then it is legal tree edges. Ah, this is tree edges. Parent of Y is X. Okay, I understand that. Okay. If discovering Y, while I'm discovering this, okay, let's make a little more complex. While discovering Y, and X was in the middle of processing. And we understand what is the discovering and the process, right? Processing done is all my adjacent edges are completely done. Discover, okay, I just discovered you. Oh, I'm gonna investigate you, right? So you just discovered the Y. And you just found that X to Y connection, Y to X connection, and it turns out it is what under the processing it. Then meaning, that is only possible by this. This is back edge. Okay. The forward edge is you just found the connection to X to Y. Oh, your processing is done. Okay. Then X is not done, or whatever. X is what discovered or no. But when you found the connection from X to Y, meaning you are checking already discovered, already processed the node, means you just found the forward edge. Clear? Okay. When the entry time of X and entry time Y, entry time of X should be smaller. Entry time of Y is a bigger. Okay. So another case, X. Okay. So this is X, this is Y. Let's say you just found this link and X and Y. Okay, let's make it different. Let's say you just found this connection. Eraser. The Y to X connection. So Y process is done, and you just found a new link from here to there. Okay. Entry time of this one, Y is earlier and X is coming. Okay. it could be the different ancestors of tree, or is a different branches. Then you just found the cross edge, the concept of this. Okay, so you can find the class of the edges by checking this 4 test. Okay, all right. So this part is a little different to the textbook, and I think it is more correct. And so I read the books multiple times. I asked the I communicate with the algorithm guys, and we updated contents to this. Okay, all right. So DFS, a tree and the backedge only. So previously BFS was tree edges and cross edges only. Okay, in the DFS, tree edge and the backedge only. Why? Okay, in the DFS, the forward edge is not possible. Let's see. In the DFS, this forward edge is not possible. Why? If you just found this path, meaning your path should be like this. Okay, so legal new tree edge is a possible, but the forwarding edge is not possible. Okay, so suppose we have a forward edge from this guy to this guy, we would have encountered 4 to 1 expanding 4. So it is definitely a back edge, right? This path is not possible. If then, it should be new edge. So no cross edge in DFS. Suppose we have a cross edge, something between 2 and 5. When expanding 2, we would discover the 5. So tree would look like this, not like cross edge. So if you think about the DFS more deeply, so DFS found this one and go to the first one, go to the first one, go to the first one, right? Then go to there, you are cutting, you complete the process from the leaf, then you're climbing up, right? Say you just found a new one, then you'll start the new one again. If you just found a cross edge is not possible, because if you just found a cross edge, meaning that it's a legal tree edge, right? Then, therefore, in the DFS, only tree edge and the back edge is possible. Okay. DFS has the tree edge and back edge only. Okay. So DFS application in finding cycle. So by implementing DFS, you can finding cycles quickly. So back edges are key to find the cycle in the undirected graph. So any back edge going from X to ancestor Y creates a cycle. Okay, we understand if we have a back edge, meaning we are creating cycle, right? Tree edge and creating up to my tree, meaning they are back edge, which means that is cycle. Okay. So look at this. You are doing this, you discover the Y, and direct parent is not X. So you discovered Y. You discovered this one should be Y. You discovered the Y. The processing is not done. You are in the state of discovering Y, and you just found X again. And direct parent of X is not Y, but you already discovered, meaning that is back edge. Back edge meaning, oh, you just found the cycle. Okay, if you can create the back edge, meaning you are detected a cycle. Clear about this? Maybe too simple for you. Okay. Okay. So let's talk about the, do you have any question about today's class? So today we learn about the, what is tree edge, and what is a back edge, and what is forward edge, and what is the cross edges. Okay. In the BFS, it is only possible to find the tree edge and cross edge. We talked about why. Okay. In a DFS, it is only able to find the tree edge and the back edge. Okay. By the characteristic of the building tree, and the depth first or breadth first, that is only possible, right? In the graph, we can classify into the 4. It will be either tree edge, forward edge, and the back edge and cross edge. Okay, so we talked about the details of the edges and details of the DFS and the BFS today. Any question about the DFS and BFS? So we are concluding DFS in here, and from next week we're going to talk about more fun thing. More fun thing meaning the backtracking, and maybe we can start to discuss about the dynamic programming. So until this point, it is more likely reviewing what you learned so far. So from right after this class, we're going to talk about a new thing. Okay. All right. Any question?
Can I ask when does forward edge occur in any other? Yeah.
So we talked about we talked about back edge and cross edge, and when this forward edge happening, is what you're saying?
Yeah.
Okay. So in the search of the in a build of the tree, there's a BFS or DFS. Let's say you're Hajun, right? HFS, Hajun FS, Hajun first search. Okay. Let's say you have any kind of the mechanism. Okay. Then let's do in this slide. Stamp of the circle. Let's say the circle. So they are connected. So undirected graph. Maybe we can talk about the directed graph, right? Let's talk about directed graph. Okay, so let's build the directed graph. Okay, so from this guy, I can go to this guy. Then this guy goes to these two guys. Okay, then this guy can go to these two guys. And where am I? This guy cannot. This guy, okay, this guy, right, goes back to, oh, no, this should be, oh, okay, this path. Let's emphasize this path. This path only. Then if I starting from this one, 1, 2, 3. Okay, so let's say, what is there? The stamp again. This one and that one. The path. This guy. This guy. Okay. Okay. So this is A, and I just built a 2, and so it's called A, B, C, D. Then it looked like A, B, it should be C, it should be B, and the D. Okay. How about this edge? B to D, then A to D. Oh, there is A to D connection too. Then if you did the DFS with the directed, then this path is possible. A to D. You already discovered them, and it turns out this path is done, and this path is done, and now this cover is done. So this is forward edge when we talk about directed. Okay, how about backward? So your question was about the forward edge. Okay, and the backward edge is something like this. This is cross edge, and B to D, and D to C. This is cross edge. So if I answer to the question, where is the forward edge happening? So when your graph is directed forward edge with the DFS, when you're doing a DFS with the directed graph, that is a possible path, right? You understand this graph? I hope so. Is it clarified? So the Hajun's question, Hajun's question was, when is the forward edge happening? Okay, you know what? We talked about undirected graph, but we talked about directed graph and doing a DFS. Okay, that path is done, that path is done. Oh, you know what? I already discovered that path, and there is connection from there to there in the middle of the discovery. There's a forward edge. Okay, when we talk about the directed, we can discover the forward edge. Okay, so in the class we talked about undirected, and your question, we discovered 3 cases. When is this the 4th case that's happening? Okay, it happened when we talk about directed graph. All right, is this satisfied?
Yes, thank you, Professor.
Okay, any question? Thank you. Hajun, right? Was it?
It's actually Hasong.
Hasong, sorry. Hasong. We don't have a Hajun. Hasong, only Hasong there. All right, any question? No? Maybe the homework and the makeup exam, if it is too tough, then we can discuss about some delays for the homework. But the midterm is fixed. Okay? I believe you guys can do this. So let's see on Monday. If it is too tough to do on time, then we can discuss about some delays for the homeworks. All right, any question? No? How about that? So the homework which given out today, let's make that due date for the Wednesday. Okay, I think that is better for your load balancing. All right, any question? No? Okay, so one comment. So the hybrid learning is back, meaning that we can meet on the classroom, then we can actually take a test, not to take an exam or online. Okay, all right. I'm very happy we can return to the hybrid learning. All right, any question about today's homework or any comment about the whole lectures?